what we started, last time, we kind of started defining the tools which will allow us to define some kind of notion of nearness actually. Okay? This nearness is a pretty important notion. Okay? We'll see how. Okay? We can already see that when you, for example, define limit in one dimension, you say that as inputs gets closer to a fixed input, the output gets closer to a particular number actually. Okay? But what do you mean by closer? Getting close or getting nearer actually. Okay? You need to have what we call a precise description of nearness. And once we have that, then you can define the limit and continuity, differentiability, all this stuff using that nearness stuff. Okay? So what we started doing last time, we started doing the very fundamentals of topology. It's not really a topology, but Euclidean topology. And then we said that, okay, we kind of defined that what do we mean by a ball centered at A with the radius R. And we also defined what is the meaning of a ball centered at A and radius R with the both form notation. So that's an open ball and that's a closed ball. We will just talk about in a minute that what we mean by something to be open and something to be what is called closed. And then we said that then imagine, actually, for example, for this we saw that in R, okay, this ball becomes an interval A minus R to A plus R, okay, and in R2 it becomes a disk actually, okay, excluding boundary, okay, and in R3 it's going to be a sphere, and in R this guy is going to be an interval A minus R to A plus R, but including boundary, and in R2 this is going to be a sphere, not sphere but disk, okay, centered at A, okay, with the radius R, including boundary in 3 dimension. It's going to be a sphere, okay, a sphere of the radius. What do you call it? It doesn't look like a sphere, but you can assume it's topologically sphere. Is it making sense? Then we defined that, okay, if you have an arbitrary subset of Rn, so S is an arbitrary subset of Rn, though I'm making the pictures in 2 dimensions, but they are actually, you have to kind of keep in the back end that you are talking about the n-dimensional object. And then we will obviously want to look at what would be the meaning of it in the 1 dimension and in the higher dimension. So S is a subset of Rn. Then we defined that what is the meaning of a point being inside S, means in the interior of S, in the exterior of S, and on the boundary of S actually. And we defined int of S as the set of all interior points, okay, and exterior, set of all exterior points, and for the boundary we use basically partial S as a symbol to denote essentially the boundary. And then we did one interesting example in which we had 2 sets, S1 and S2. The good thing and interesting thing about those sets S1 and S2 was that they both have the same interior, same boundary and same exterior, but yet they are different actually. Okay? So what was the fundamental difference between both of 2 sets is that basically one was open and other is closed. So I would like to precisely define In other words, one includes the boundary and other doesn't include the boundary. So I'm going to call this as an open set, while this is an example of a closed set actually. Okay? Alright, so okay, so let me define precisely, and maybe you can tell the definition that what was going to be the meaning of having an open set. So consider you have a subset S that is a subset of Rn, okay, and you're going to call this set S an open set if what happens? If
all points lies inside the interior of S is equal to S.
That's a very good good characterization. That if the interior of S is equal to S, this is one of the we can treat this as a definition, but I want to prove this as a theorem actually. Okay, so okay, you can treat this as a consequence of something actually. Okay, so what if something is open, we say that it doesn't includes its boundary. Okay, so if I have to say mathematically that a set does not include its boundary, how should I say it mathematically?
S intersection boundary does that.
Exactly. So I should say that S and the boundary of the set have nothing to do with each other. Okay, they have nothing in common. Is it making sense? And I'm going to say the same set is a closed set if the boundary is included in the set. And how should I say it mathematically? Okay, so you can say S is equal to interior of S, union boundary of S, but okay, that I can treat this as definition, fine, okay, but there is another thing.
इसी केस में इसकी जो इंटरसेक्शन होगी वो बाउंड्री का लेवल एस इंटरसेक्शन रहता है बाउंड्री पॉइंट्स का जो सेट होगा वो सबसेट होगा.
Exactly, so that's what you can say. So you can say that the boundary of the set is included in the set. Okay, so if the boundary of the set is included in the set, you're going to call that set a closed set, and if a boundary of a set is not included in the set, as an empty intersection with the set, we're going to call it an open set. Okay, and there's a famous joke in what we call topology. It's called, what's the difference between a set and a door? So what is the difference between set and a door? That we know about a door that it is either closed or open. Okay? But a set can be open and closed at the same time, and it could be something which is neither open nor closed, or it could be only open and open closed, could be closed as well. Okay? So that's what makes a set different from door, that door is either open or closed. Okay? While if you take a subset of Rn, it could be open, it could be closed, it could be like the door half open and half closed. It could be the more stranger, it could be open and the closed at the same time. Okay? And it could be a kind of a set that is neither open nor closed. Okay? So let's talk about an example which is say half open and half closed, for example. One of the example of the open set is the open disk. Okay? Open disk will prove that this open ball that we have basically is an open set. It doesn't include the boundary, and the closed ball is basically an example of a closed set actually. Okay? But let's think about some of the examples which are both open and closed, and which are neither, and which are half open and half closed. some openings, some closed. Okay, something like that. So consider an example. Here's an example. So consider a set in R2. It's a collection of the points. Okay? And what's a good thing about those points? That with regards to x, it satisfies the inequality x less than or equal to 1. And with y, it satisfies the inequality that y is strictly less than 1. Okay? So it's gonna be basically, what do you say, the interval. You can say that if you open it, this is nothing, this is just the cross product of the interval -1 to 1 with -1 to 1. Right? So you can choose x from here. So if you can choose x from here, x can be anything between -1 and 1. In other words, satisfies this inequality. And y is going to be chosen from here. So y can be anything between -1 and 1. In other words, it satisfies this inequality. Is that making sense? So if you're going to plot it, how does it going to look like? So x equal to -1 is where? So it's maybe here, -1 and this +1. So the lines are included. Okay. So x equal to -1 is this entire line, and x equal to +1 is this, what do you say, entire line. And where would be the y equal to 1? So maybe y equal to 1 is here, and y equal to -1 is somewhere here. So that's okay. Y equal to 1 is not included, so I'll make it dotted. So if I'm making something dotted, I mean that I'm not interested in that line, so everything except that, and a dotted line here. Okay. So what is this S3? So S3 is basically this. Okay. Now what you can say, what interesting things you can say about S3. That S3 is a set which is neither open nor closed. You can't say that it's, what do you call, closed. Why? Because, this part of the boundary is not subset of S. And you can't say it's open, okay? Because the set intersects with the boundary. So it's neither open nor closed set. So everything here is in S3. Is it making sense? A little bit? Good. Okay, or you can also treat it as half open, half closed. Okay, that, What do you mean by half? Okay. You can call it half open, half closed. Okay. Why these things are important, we'll see in a bit. That all these basic definition allows us to what do you call, define the notion of limit and hence continuity and the rest of the things actually. All right, so let's move on. So what next we would like to do, we would like to talk about some of the very obvious properties, for example, which some of these guys spotted. For example, someone said that, I said that a set is open if it is same as its interior actually. Okay? So, question is, can we prove it? Okay, it looks intuitive, but the question is, can we prove it? A set is closed if it is the union of interior and its boundary. Okay? So in other words, all such consequences, I would like to write a proposition, and I want to collect all such properties of this interior, exterior, and how they play with each other in the form of a proposition, and I would like to prove it, and you can keep it for rest of the discussion actually. Okay. So one of the things that you might already have realized that the names that has been given to the terms has a real world meaning behind them, has an intuitive meaning behind them. So when you are calling something boundary, it looks like a boundary of a region actually. So it's something very intuitive. Are you getting the point? Especially when you are in, for example, Rn, I don't know that how does this set is going to look like, because I have no conception of a higher dimension than maybe 4 or 5 actually. Okay. So how does the boundaries and the say interior and exterior would look like? That would be for example, let me give you an example. So that's a 3-dimensional object. Okay. How does, so this desk is a 3-dimensional object. Okay, or maybe this page or the set of page is a 3-dimensional object. Okay. What is the boundary of a 3-dimensional object? So for example, for a 2-dimensional object, I know that boundaries are lines. A circle has a line boundary in a region. Huh? And how about in 3 dimension?
outermost layer sir.
Outermost layer क्या है?
Sir, उनकी boundaries 2-dimensional होंगी sir.
वो surfaces होंगे. So they are going to be something surface. Surfaces for a 3-dimensional object, the surfaces are roughly the boundaries for, okay, boundaries for 3-dimensional object. Now here's the question: how about a 4-dimensional object? A 4-dimensional object is going to be some kind of object with the boundaries whose boundaries are 3-dimensional. You can imagine that already it becomes complicated actually. What do you mean by having? So we can conceptualize, okay, boundary as a surface or a line, but what is the meaning of having a 3-dimensional boundary? It would be a very interesting thing actually to think of.
One-dimensional object boundary.
One-dimensional objects are lines, so they are going to be points and points. For example, अगर आपके पास interval है, so if you have interval A to B, then the boundaries are, the end points. The points, and the point is what 0-dimensional object. So the boundary of a higher dimensional object is n minus 1 dimensional. So we have n minus 1 dimensional boundary. Anyway, so when you are talking about Rn, it looks so innocent, something very simple, intuitive, but it's you are talking about a crazy kind of object J.
So how point is 0-dimensional?
In other words, okay, so if you define that why the line is 1-dimensional, okay. In other words, if I have a tip of this point, so I have this point actually, if I treat this tip as a point, then I can move this point in any dimension. So in one direction it's going to produce the line actually. Okay? And so I'm going to call it 1-dimensional actually. So in order to produce a line, you have to just move in one particular way. How about if you have to move in plane? So you can have in order to reach to a point, you have to go horizontally and vertically, or in some other ways where you need 2 things actually, or 2 kind of motions. Okay, so you're going to call it a 2-dimensional. The question: in order to express a point, how you need to move? You don't have to move. So roughly you can say, point is a very complicated thing actually. It's a very complicated thing. Okay? So with analogies you can say that okay, it's a 0-dimensional. You don't have to move at all. Okay? Anyways, let's move on. Let me write a proposition and let me prove this proposition. I will try to show it through mathematically. We have to learn mathematics better. Okay? Intuition is not enough. Intuition is good. It helps you to understand that okay, what the heck you are doing. Otherwise, theorems becomes very nasty. You have no idea what you are doing, but you are doing actually. Okay, but intuition helps you. But intuition is not enough. You have to learn to write and to give the precise argumentation. So here's a proposition that I'm interested in. Imagine I have 3 parts of Rn. So S and S1 and S2 are 3 chunks of Rn. Okay, so they are basically 3 subsets of Rn, 3 parts of Rn, and I would like to show, okay, that what brother proposed, that S is open. So we know what is the definition of open, that it doesn't intersect with the boundary. I can show that this is true if and only if the interior of S only is equal to the entire S. In other words, S is boundaryless. In other words, it's equal to its, its interior actually. Okay, so you can, if you wish, you can also treat this as a definition. So what's a good thing about if and only if? Whenever you prove something if and only if, you can replace it with a definition. Okay, so either you can treat this as definition or you can treat this as definition, it's fine. So it's a kind of characterization actually. Okay, that's what a good thing about the if and only if statements is. The second conclusion that I would like to say is that F is closed. This was also very intuitively, proposed by one of the guys who said that if you take interior of the set, okay, and you put boundary into it, you should get the set. So if a set is closed, then you can construct it through adding boundary and the interior of it. It's very natural thing to do. So the third part that I would like to do is that this is something very interesting. If, in other words, okay, open and closed things are how they are related with each other, and just look at the picture, for example, any of the picture open and closed, and see that whether this looks true or not. So if S is open, so if set is open, then its complement is closed. So if a set is open, its complement must be closed. So this looks reasonable?
Yes.
So imagine, this disk is an open disk actually. Okay? So if I take the complement of it, what's going to happen? The complement is going to contain the boundary. Okay? And that boundary is going to be the boundary of this. So if a set is open, its complement must be closed, and if a set is closed, its complement must be open. Okay? And then, as usual, once we create things, then we also do their algebra. So you can basically ask a question. Imagine you have two open sets. What if you combine them, or what if you intersect them? Will they still remain open or still remain closed? So the answer is yes, actually. Okay? So if S1 and S2 are open, then what? S1 intersection S2 and S1 union S2, their combination is also open. Okay? And E, you can have a similar statement for closed sets actually, that if you have two sets which includes a boundary and you combine them, they should have kind of a, boundary should be as well actually. So in other words, if two sets are closed, their union should, an intersection should also be closed. Okay? So let me prove some of these, and maybe I can leave some for you to figure it out, that how to prove them. And so how many of people can see this part of the code? Is it okay? Everyone is happy with it?
Yes.
In the corner? Can you see it?
Yes.
So let's begin with the proof. So how do you prove an if and only if statement actually? So you have to do the both ways. So let me prove, for example, the forward side actually. Okay? In other words, let me assume that S is open. Okay, I need to show that interior of S is equal to S actually. Okay? So, okay, suppose let S is open, and I need to show, we need to that interior is equal to S. Okay? So I have to show the equality of the sets. So interior is a set and S is a set, and you have to show the equality of the sets. Okay? Mathematical thinking is coming in that. Now, how to show the equality of two sets? You have to show the subset of it actually. Okay? Interior of S is a subset of S is obvious. It's true by definition actually. Okay, so what is the definition of interior of S? So interior of S is the, okay, let's try to show it. You can show it out. Do you think that this is obvious?
Yes.
That's it. Always prove the obvious things. Okay? So always carefully think about that, why this is the case actually. Okay? Now let me show, okay, so must verify this actually. So whenever I put out this mark of exclamation, it means that verify. Okay? Even though it follows from definition, but how? Make sure, convince yourself that. The next thing that I would like to show that S is the subset of the interior of S. So how can I show it? I need to pick a bicep from S, and I need to show that that same bicep also lives in interior of S. So let me pick, for example, what? Some point, say P from S, maybe A from S. Okay? And I would like to show that this A is a point in the interior. Okay? Now if A is a subset of a point in S, so what thing we know about the S is what?
Open.
So it's an open set. And what's the definition of an open set? So if you have a point in an open set, okay, what you can do?
Open ball.
You can you can draw a ball around that point at the center with some radius r, such that the ball is contained entirely in the set. Okay? So let A is a point in S. So you must write it as S is open. Okay? So you can find a positive radius such that if you draw a ball, an open ball at A with the radius S, this is contained in the S. Okay? This is contained in the S. Now I'm asking from you, what is the definition of a point to go in the interior? So what's the definition of an interior point? So interior point is a point on which you can draw a ball which contains, which is contained entirely in the set actually. Okay? So since I am able to draw a ball on A with the radius r, and this ball is entirely contained in, S, so I would say this implies that A is an element in interior of S actually. So it's an interior point. It satisfies the definition of being interior actually. Is it making sense? How about converse? Let's think about converse. Converse is what? Converse is that, okay, assume that interior of S is S. Can we show it it's open? Okay. Here's the thing. So the next part is that assume that interior of S is equal to S, and we need to show that S is open. And how can I show open? So what is the definition of being open set? That if you take the set and intersect with the boundary of S, you shouldn't get anything. That's what is the definition of being an open set. Okay. Now you are saying someone that, you know, if something set, if a set satisfies this, this is going to happen. Okay? You are making pictures and trying to convince him, but he is still not, you know, convinced. So what are you going to do? You're going to say,